Hello everyone, and today we're back again on a Division 2 round on CodeForces this time. I'm using the CPH Judge as always to parse my problems and to test them out. Yeah, so um, check out the other videos as well on my channel. There are some explanatory videos in competitive programming electronics. But yeah, as usual, usually I'm not going to talk a lot on this Div 2 contest because it, oops, have I not logged in? Um, because I want to solve the problems quickly. So you're given a sequence A and sequence B is called good if it satisfies the following condition. Bi is a positive integer, Bi is not equal to Ai, so okay. And then all of these are increasing or find the minimum value of Bn among all good sequences of Bn. Okay, so Bn. So first the first increasing sequence, but if one of these match with A, then I will shift it one more, and I will do this repeatedly. So this will be optimal. Let's go on the mirror. Let's see if there's faster. Okay, B. There are n sets. The union we call set attainable. Attainable if it is possible to choose pretest passed on A. If it is possible to choose some of the sets so that S is equal to their union. If you choose none of the SI sets, their union is an empty. Find the maximum number of elements in an attainable S such that S is not equal to the union of this. Okay. If S is not equal to the union, so there's 100 and there's 50-50. Okay, let's think about this. If S cannot be equal to their union, S needs to be some element smaller than their union. So to delete some element. And if I delete this element, are sets created can this exist in a sense of the way? We want to ask, is it so there are n sets so sets at I resize k okay. Now if it's not their union, so we take one element out and then we say, is there some set of these that creates, or no, not some element out. The elements are up to 50, so we can do frequency on which sets are attainable, and we will delete the element which is in only one of the sets or in the smallest number. Then the answer is the minimum. The answer, so we'll delete the sets. No, should we delete the sets with the smallest element? So what is the maximum number of elements in an obtainable S? Wait, we want only one set to be deleted, right? Okay, this is simple. We want one set to be deleted. And now we just want to say that I will add first all of these elements. Map at element plus, then I will remove them and then add them again. Minus. Are they all distinct? Yeah. Okay, and then the answer so for this set, I delete all of the elements that are inside the map and then add them again. Why is it +1? I should debug this problem, I don't know why. Okay, this is 5. Why is it 4? Oh, set not equal to n. Oh, if mp dot size is smaller than initial size. but here what we do here? Oh, can we delete more? I mean, we can delete more, but is it optimal? Weird. How is this optimal? The union that is not equal to the set. So if the frequency is this, I want to delete the most. Let me go back to the frequency. If the frequency, if we want to delete only sets that has the smallest frequency, only element smallest, that does not guarantee that the sets that have the most unique numbers. Can we make a graph out of this and then what? Well, this is a good problem, I just don't see. Number of elements in SI file. There's 50 elements. Number of elements. Let's assume that we make a graph, then what? How do we make a graph? So one element is connected to the other. To what sets it is, and then that can have at most 50 elements. Whoa. How am I stuck here? For each of the element, let's say it is not in the set, right? It is not in the end set. So if I don't want it to be in the end set, then what sets I need to remove? For each of the element in union, what sets I need to remove? If I don't want it to be there. If so, sets for each of the element if union dot if sets at I count so there's at most 50 elements times 50 sets times log, which is nothing. So count element want to remove this set, right? So if it's not failed, okay, so this is 50 times nothing. Oh, this is if it's not counted. Here, if it's not counted, then we want to break. So if it's not counted inside of the set, then we want all of the elements to be inserted. So this is times 50 and this is times 100. I don't know why it took me so long, but I hope this passes on time. Okay. This was slow, but okay. Whatever. They're in cards stacked So can I see the test, the pretest? Can see which time. Oh, it took really fast. Okay. See, there are n cards decked in the deck. Initially, AI is written on the I card at the top. The value written on the card does not change. You will play a game. Initially, your score is 0. In each turn, you can do one of the following operations. Choose an odd positive integer I, which is not greater than the number of cards left in the deck. Remove I card from the top of the deck and add the number written on the card to your score. The remaining top cards will be re-indexed. Choose an even positive integer I, which is not greater than the... Remove them. So either a positive or an even, so even doesn't add it. Positive, odd adds it. And the game, you do not have to remove any other card. Okay, what is the maximum score you can get a game at? If an integer I is... Oh, okay, what the fuck? Okay. Okay, because there are negative numbers, I assume there will be negative numbers. So, okay, yeah. No, let's read the input. So I assume sometimes you need to remove a negative number, or you need to cleverly arrange them in an even and positive manner. Okay, so what happens? What happens? It happens such that when I remove a card, all of the... In the first turn, you choose I2, your 0 remains in the numbers written on the card top becomes... Second turn, you choose 3, 5, your score is 5. Can I somehow... He wants to get the score of 5. That's why he removes this number and doesn't change, and then the 5 gets here. So there is essentially what he wants to say is that there are some positions, right? And at the odd positions, you get points, right? Here you get points. And here you remain equal. I mean, you sum up these numbers. So if there's a negative number at an equal position, so let's start from the back. If here is some number that I want to get, I will get this number. But here, if there's some number I want to get, so let's say here's this 5, right? But I can't get it here. This plus number says this plus says I will get this, but this is smaller, right? So I kind of don't want to get it. So there's -3 or something, right? Then here this I, if I get this, so this says okay, I will get this, but I will shift all of these numbers that I did not get previously to positions where I can get them. So I need to store two things. I need to start from the back and store in the odd positions. So I just want to get positive numbers. I don't want to get negative numbers, right? Yeah, so technically I want to start, because negative number I can get it, but when I get it I will shift and get all of the other numbers as well. So I will start from n minus 1, go down, and now here's the thing. I need to keep track on the integers in the, I'll say remaining, this here, what is remaining, and what get. Now if I is odd, this is get, is even, for us it's get, and this is remaining. So in get I will decide, no, in remaining I will decide whether or not to remain. In get I will say, okay, if it's a positive number, if AI is positive number, I'll get it. And shift all right numbers. So this, so now these which are remaining can be get as well. So answer, I will get even the remaining numbers, right? Else, if it's a negative number in this position where we want to get it, we don't want to do anything with it. We may want to shift it. We may want to get it if all of the remaining numbers are to be get. So maybe we want to get it just so we get the remaining. But this is now deep, you know. It's now turned into a deep P. I would assume. Either you shift. Yeah, it has to be deep, I think. So you have two states maybe in the DP. One state is where nothing here is shifted. And the other state is where... No. Wait. Maybe we want to get it. Just so we get the remaining. So this, if I get this, the remaining here will also get. So, right. Okay, the remaining will be get the remaining. But there could exist a smaller number here where we will shift them all and a smaller negative number we'll shift them all and get a more bigger remaining. Right, is that correct? So what if it's a DP? What if it's DP? If I'm here, I want to know whether or not this is shifted. Or do I want to do it the other way around? So given some prior state, I know that either this is bought or this is not bought. Right? This is shifted or this is not shifted. And then here we want to say, okay, I will buy this and shift this again, or I won't buy this and shift this again. Okay, let's try this. dp at I and some shift. Now the shift is, wait, the shift, this is, we can choose this either to buy it or not to buy it, right? Then if I buy it, I will shift it. So it's I but I need to do this for both shifts, right? So I will say this. dp of 0 and 0, so not shifted, is A of I. Is I don't buy anything, right? dp of 0 and 0, now I buy A of I, A of 0. Now shift, here we say that dp of I and either okay, the dp of I minus 1 and some shift, right? So first, let's say we don't buy. Then this shift remains. Then dp of I and this shift remains. And we don't buy. dp of I and shift 1, dp of I minus with this shift plus, and now here's the tricky part is, first of all, I divided by 2 equals 0. This is one thing, if it's true, if I can gain this. But then this is some shifted. So this is something, some shifted. Like this, I think. If this is if it's previously shifted. Oh, then this is times the element of A of I, right? 4. This is 4. This is shift by this and then by this. I see. It could be the other way around. If it's the other way, if I start from the back of the array and I say that if I buy this, then sometimes it would be nicer probably to buy the first one then to shift it, right? Is it possible? Is it possible that this is the case? Okay, this reminds me of one problem from Yandex or something, where like you had to keep two different things. You had to do some odd, some DP for the odd things and some DP for the even things. And you had to calculate as if in the as like you switch places. You say you start from the back and you say the following. First, we calculate DP where pluses are on the odd and where minuses are on the even. And we do, right, how would that look? So let's say I'm here in some element. There's some other elements to my right. And I will say, okay, what is if here are some pluses, or if here are some pluses, I have calculated two different DPs. And I say this, if I buy this element, I either get the DP if I buy this element, I get this DP, because I can shift them and do some stuff with it. Or if I don't buy this element, then I get this DP, which is the original one. Right? Well, let's try something like this. So it's still n and two-dimensional, but at n minus 1 it depends now on n minus 1. Is n minus, if it's n minus 1 divisible by 2, and what is this now, 0? I mean there's no shift, let's see. It means, okay, 0, it means that here, let's say it's empty. Let's say this. And 1, it goes with 1, with this n minus 1. Then we start at n minus 1. We go to 0 and we say a little bit different. We say dp of, okay, we don't start n minus 1 but n minus 2. The maximum will be of dp of 0 and 0 and dp of 0 and 1. And here all we say is, let's suppose that here there is a plus at the end. No, remaining, right? Let's suppose here there's a remaining. At the end there is this action. Because here it's 1. It means that it's a plus. Let's suppose that this is the case. Then want to maximize this with something that this is with the case. Okay, so we maximize it with the dp of I plus 1, where this is 1. Let's say that here is 1, and then we maximize it to dp of I plus 1, and we don't buy this element. So if this is plus and this is minus, we don't shift anything. We just say dp of 0 and And that's pretty much it. Or we buy this element, in which case we say that but if here is this and we buy an if here is this and we buy this element, then here is like the maximum of this and this. So this is here, but in case here we want to buy this element, then of course this is a plus, right? And we want to say that this is, we buy this element, right? So there's this. This is AI times whether or not this is divisible. It's very important. No. This is not. No, it's not important. Now it's not important because we say that. Okay, so this we can get without buying the element, right? This we can get if I buy this first something here, then I buy this element. Get plus AI, but also did I miss something? Of course I did. So there's plus and minus, right? I mean plus and remaining. So there's this case where, okay, case where I'm plus, or case where I'm remaining, is case where I'm remaining. Here is plus, or I'm remaining and here's remaining, because I can buy all of these stuff, then this, or I can buy this and then all of these are shifted here. So this is the case, but in both cases I don't get anything here. Where on the other hand, if there's a plus, I have, in one case I have where I buy the element, where I don't buy the element here. I do something here, I don't care, but I don't buy this element, right? But in the other case is where I buy this element, and now first I buy all of these elements, then I buy this element. Or there's a case where I buy this element and I buy all of these elements, like that. Okay, why is this the case? where I don't buy this element, where I buy this element, I buy this element. I don't know what is going on here, but this essentially is the DP, I think. Come on. Okay, pretest pass. Okay, this is not great since I'm a bit behind, but isn't that bad. Okay, now 3 XOR is gonna be a fun problem, definitely. You're given a tree, labeled versus labeled from 1 to n, and AI is written on each vertex. You want to make all AIs equal by performing some spells. Suppose you root the tree at some vertex. On each spell, you can select any vertex v and any non-negative integer c. Then for all vertices in the sub tree of v, you do this. The cost of this spell is s times c, where s is the number of vertices in the subtree. Okay. And the c is this. Let MR be the minimum possible total cost required to make all AI equal. All AI equal. If vertex R is chosen as the tree, find this. Suppose vertex R is chosen as the root tree. Yeah, but vertex R is if vertex R is chosen, is vertex R given? No, I don't see vertex R given anywhere. So there's n. There are the these here, and then there is this. So vertex R is not given. I can root them anywhere. Suppose you root the tree at some vertex. Vertex R is chosen as the root of the tree. Find. Oh, for each of them. For each of them is the root. Okay. Now this got a lot more serious. So for each vertex, suppose that vertex is the root, and I can perform these spells. Now each spell costs with the size of this thing. So I would say first, okay, so let's try with some fixed R. Then I have some sub arrays that represent my tree, right? So I can linearize this tree. Then what I can do is I essentially say from here to here, the size times some c, I can change this. Well, that means that if the size here, so that means kind of the size here doesn't matter. It means that, oh, it doesn't quite mean, you cannot just take some intermediate vertex. You can take the leaf nodes, but you can't take the intermediate vertex itself. So the subarrays have to be, if a node is here, then okay, then this suggests something to do with the leaf nodes. And they're only case where you can just change them to some, like, with some C. But because you have to change them all, it means that for, okay, so for okay, so I know this problem, then E1 is quite a long problem. Quite a long problem. Maybe it's more. Let's think about it. There are 2 to the 20. So something is very, very fishy. 2 to the 20 is 1 million. 1 million. Something is fishy here. There will be one vertex which will remain the same. Okay, first observation. There will be one vertex which will remain the same. Let's pick this vertex that will remain the same. Is this vertex going to be the root? Is the root of the tree? The tree will always like remain the same. The first spell 1, 2, 2, 3, 2, 4. Can we claim that the root remains the same? If I change the root, I change all of the vertices, which means that I don't ever want to change the root. Due to the commutativity of the sum of this operation, I can, the distributive thing here, I will never change the root. So in case I want to say what is the minimum, so we can rephrase this problem and what is the minimum cost to change all vertices to AI and I is while I being root, while I is root. This is my thing. So how much does it require to change all of this? And they all go up to 1 million, right? There's something weird with these AIs, why they go up to 1 million. There's something very weird. Okay, so let's say that I have a subtree, right? So let's say that I have a node. this node can be influenced by something from above or itself. So either something coming from above can influence this node or himself and influencing the whole tree, the whole subtree. Okay, so say that which nodes have to change? Which nodes have to change? Each node will only change at most once. I mean, it will change more times, but you will only use it in one. Not really. Not really. No, it won't be one contribution. The node here could be changed multiple times from above. How much time do we have? Oh, no. Could be changed multiple times, right? Let's take a look at the path. I have some values here. Then it means that the value, let's say some value here, and this is some other value. And now the root node is something like this. So I want to make this the same as the root node, right? So I have to, each of these children as the root node, I have to apply the XOR between. So I have to apply roots XOR AR XOR myself, a child, and then this is times my subtree. And I have to do this for all of my children. Then propagating back here, now this here guy changes with this XOR. So this guy here essentially gets this XOR, roots XOR, and this XOR. So this guy becomes already a root XOR, embedded with this and himself. So I have to change this guy with his parent and himself times the size. And then I continue here. So I only have two things, the parent XOR and himself. Okay, This operation is non-distributive or something like that. At least I don't think it is distributive. It's not bitwises. No. But okay, so we have this connection. So each edge essentially will get us in some tree. So each edge will contribute the change in the XOR, and so each edge will contribute the change in XOR between these two times some. So each edge contributes AU XOR AV times sum of something. Now, what is this something? It's okay, so some trees will have this, some trees will have this subtree. So there's some subtree, so okay, each edge will contribute U, V times, and now here will be the size of the subtree U times how many, so how many trees will have this subtree? We'll have them the size of the subtree V, and then plus the size of the subtree U times the size of the subtree V times the size of the subtree U. So this will do this. Now this here is easily calculatable, such that this is easily calculatable. So I think we can is it guaranteed that all of them are connected? Okay, so we have the subtree sizes, then for each edge. Answer is so for each edge. Answer is the A of u XOR A of B times the sub size of u subsize of u times 2. Oh, but you have to do this for all. Okay, so wait, is the sum correct though? Of course, adjacency clear. Is the sum correct? What is this? This not correct. This 36. Yeah, of course it's not correct because every node would be a root node, and such a root node won't change anything. So every node I like, I think -1 here should be the case. But no. This is, wait. Okay, so wait, my answer is smaller than what's the sum of all of these, right? Okay, let's say, okay, in this root node, in this scenario, we have all of these edges that are not in the root node, so that are not of these. All of these edges will, each edge will get me each edge will get me the XOR times the subtree from u, on this point from u, if this is u. So, right, so my idea is each edge will pre-calculate. So So for each node, you want to calculate what will be the subtree if some else is the, if this is a root node, right? Then if myself is a root, try calculate then and then only like subtract something. We need definitely to subtract these from the root node here. These edges. Okay, two DFSs maybe. One DFS that finds, okay, so the other DFS, when I go down, I want to add this edge and all of the other things here, all of the cost of the other things will be incremented by one. If this is like, if there's some sum that is a cost, this will be incremented by itself. Or no? Well, I add this node into the mix. It means that not only add now these edges, what does the math look like here? The math, we have some cost here. Let's say this is S. These remain totally the same cost, but now this guy will introduce its or XOR with these children here. And the cost will be so that each of his children will actually make cost from the cost. The cost here and plus the cost here. But then when I return back, the cost will be added on that side, and then okay. So okay, let's think about this. For one node, there are some children nodes, right? And let's choose this children node to be a root. If this is a root node, then it means all of the other children nodes, we know how to calculate their cost with relative to the parent. We know how to do that. This root node will have some pre-calculated cost for being a root node. What if this is a root node? This cost for being a root node is something. So cost root should be something that is pre-calculated. And now we need to, on the second DFS, we need to add what is this cost here. Okay, let's archive this. Duplicate. Okay, so so I have DFS1, okay, the subsizes, right? Then one cost as being the root. But this is in perspective with being like 0 being a root, being the major root node. If that makes sense. So the cost here, okay, how to calculate this cost? Oh, this is not easy at all. Wait, this edge has something here, right? So the cost of all of these to be changed. So if I have AI here, let's just first do this. And AC and AC one. Here I want to change this to AR. So I do AC and I XOR that. Here I XOR that with AC XOR AR. Now this becomes AR. Now here, because this becomes AR, this also becomes AC XOR AR. So here I just want to XOR then AC XOR AC1, because here I want to negate this AC, which is being XORed here. So in fact, yes, that's true. I think this would go for for AC2. If it's AC2, this AR will propagate itself, but this here XOR this will go down, but this will now remain. And then AC. So okay, so that makes sense. And then okay, so how to calculate if this is the root node? I have some children. I know what is the cost for them being root nodes. I know what is the cost for them being root nodes. Is all of these being XORed with this. Now this guy has to XOR with myself, right? So okay, DFS1. I know what is DFSB, so I know the cost here to be this, and my cost root at U is going to be this, but also is the A at U XOR A at B. Now A here has to be times the subsize of B. So this is another thing that I need to add to the calls, because I want to make this the root. Okay, now DFS1 is going to be called again from 0 to -1. Now DFS2 is a little bit more complicated. And the answer array should be cleared here. DFS2, when this is called, it's a little bit more complicated, but then I just print in the answer array. It's quite easy. But DFS2 says the following. What if, so says the following, okay, so I have this cost below, but I don't know what is the cost for, so what if, okay, so this node, and I'm dividing it in this node. I say, what is the cost? I say the following thing. So V adjacency at U, V is parent continuum. Then I have all of these costs. So this is like, let's say T. I want to remove the parent here from the, or just maybe just skip, let's say that Okay, so we'll do this. So A of t will be the cost rooted v. So this being a root node, then the following for the suffix. And now again for this. Oops. So for each of these I want to say that, okay, so now not only that, now there has to be the idea that the cost of all of this is being root nodes. Wait, we can just say that this is a root node, right? And you have the cost to all of this minus this here. I don't need the suffixes and prefixes. I can say that then the answer if v is parent is continuous, answer at v is going to be equal to the cost rooted myself u minus a of u times so wait the root node minus the n minus the subtree of v. I think minus the subtree of v of yeah, and minus the subtree of v is everything except v. So everything here has to go. This is the cost of the root node, but what if this is the root node? Then the cost of 0 is cost root of 0, something like this. Answer. What happens at the end? Well, nothing, right? Cost of u is I want to make this the root node, and I do this. If I want to make this the root node, and this is I want to make this the root node, then this cost is 0 down, but then the cost making this the root node is well, there's cost that propagates down, right? No, this is not correct. Oh, wait, can I just see? Wait, how? Why? Of course, this is yeah. So we need to propagate the cost down. The cost is propagated down when this is the cost of. So what if here there's something here? The cost is propagated such that it's the sum. Yes, so it's the sum of all costs so it's the sum of all costs without myself. So this is prefix. Okay, so this is something a little bit different. Cost is p plus s, and then if p so int p is I 0 0, otherwise it's prefix I minus 1. L actually I is t minus 1, then it's 0, otherwise suffix I plus 1. So we have this. We then propagate the cost down. The suffixes are fine. Adjacency at u at I. That's what we're propagating down. These are the suffixes. This is the cost. Cost being this root node. Now my question is this the cost? So let's say that this here, then the cost is being this root node, which has all of these edges. Cost being this node. let's try it like this. A of I. Now we need this cost plus the cost of the road. So let's see what is each cost. These are being this is the cost of the road. It's being root nodes. Now we need the answer to update. The answer to update the answer. Yeah, so we're here, right? We have some cost from upstairs, right? And then we need to come, we update the answer by saying, okay, what's the cost in all of the, what's the cost is if I'm a root node. The answer is u is the cost at root at u plus my cost from above, right? My cost from above is everything except this, and then plus a of u xor a of p times n minus subsize of u, I think. N minus subsize of u plus 1. No. N minus the subsize of u is whatever this is, and then this is my cost to add this edge. Can also add it here. N minus my subsize of u. Oh, this the cost here AI. No, so the AI is what we are pushing down, right? Well, we're pushing down everything except So AI is cost of is answer at u except the cost root of now I want to just to push here. I don't know if I even need this stuff. I mean, I want to push the answer to u minus a of u XOR a of v times, in my case, it is the subsize of v minus this is the answer at u minus cost root b. Yeah, this should work. You probably saw it first time, yes. Yeah, I got a little bit rating points, but yeah, slow this round, slow. E1, let's try E1. My friend here didn't manage to solve it, but E1, maybe he will. E1. This is an easy version. The difference between the two versions, if you do not have to minimize the number of operations, you can make any hack. You have two permutations. Initially, PI is this, and QJ is BJ. So you can apply following operation. One operation, P and Q will change accordingly to the drift steps. You choose integers I, J, which satisfy. Okay. The permutation P is partitioned into three parts. Pi as a pivot. The left part is formed by elements P1 to Pi minus 1. The middle part is a single element, and the right part, okay, performed formally after this step, P will become swap the left and the right parts of the permutation. Perform the same transformation on Q with index J. Formally after this step, your goal is to simultaneously make Pi equal I for this and Pj. So you're given permutations and you need to create the identity permutation in both of them and find any valid way to achieve this goal using the most 10,000 operation. So there are 25. Okay, we'll have to minimize the operation. So there's some strategy here involved. 2,500. but you can choose integers such that they're equal to 1 as well, and then this would swap this integer to the back of the permutation essentially, or vice versa. This will swap them because both can be chosen I and j independently. I would think that they don't really you could choose, like, if you sort one of the permutations, then the other permutation will be then you can always choose two elements and you can just can you, yeah, you can choose first and the last element always, and then this will just bring it back to normal. So the idea is how you can sort one permutation. That's the problem. Now sorting one permutation, choose the minimum. When the minimum element is chosen, can you always achieve the problem possible that there exists? So in the first thing here, first operation is 3 and j4. This becomes this and kill the content. Second operation, it's swap them. So this becomes here, then this. So yeah, so each permutation can be broken down into some several yeah, each permutation can be broken down into increasing things, and then we have some increasing things. And when I choose an element here, you swap these things and these things. What does it mean that this element becomes the center? So what if this is 1? Then, okay, so you swap this. So this becomes here 1. And now this doesn't exist. But then let's say this is 2. And can I swap this? So 2 becomes, now to get 2 to here is first you have to swap maybe this element. Get the 2 and then swap it back. So yeah, something like that. Not sure. But I don't have time to code it, so I will just clean up this here mess that I wrote with suffixes. I don't know, I like problem D. It's fine. This is, yeah, I think because there's 22, what you do is like it's four times the maximum of this and this, because there's some strategy where each element you kind of swap it. And okay, so let's assume that we want to get P10 to P2. Then P10 is here, so something here, and P2 is here. So there, I'm interested in P2, P10, and this. So if I swap this with this, it turns out that P10 goes, it turns out that, wait, I will copy this. Turns out that this is 2, this is 10. This goes here, this goes over here. And now I want to swap this and this, maybe. No, we want to swap. Let's assume that we swap this and this. If I swap now this and that. We swapped around 10. Now, what about if I swap here? Now 10 is in the place of 2, 2 is in the place of 10, and these here are both. So yeah, these are the 4 operations that you want, 3 operations that you need to do in order to swap 2 numbers. And now the problem is, the problem is straightforward, and we're gonna swap the least amount of numbers we can. And this may solve even E2. This may solve even E2. Using minimum, I don't know how to prove that this is minimum number of operations, but I think this should be kind of correct. Minimum number of swaps, then you use this kind of technique to swap around numbers. Yeah, I'm not sure exactly, but I think that's these are the solutions. So yeah, that was cool. Thank you guys so much for watching, and I see you in the next round.